All right, so the plan for today, we have quite a bit on the schedule. So finish up 3-2, which really is these last three things, the fairly short things, not nearly as involved as, say, um, talking about the variance and standard deviation, but just a couple of small things, the empirical normal rule, Chebyshev's theorem, and the range rule of thumb. Just an introduction to Chebyshev's theorem. We're not going to prove this. We are going to cover some important proofs at the end of chapter 5. So once we've developed a little more material, a little bit more syntax and notation and so on, just to make things a little cleaner, that's when we're going to cover some of these proofs. So we're going to present Chebyshev's theorem, but not prove it. And then moving into measures of position. Note again that supplement on geometric mean and harmonic mean was posted this past weekend, and section 3.1 homework was moved to this coming Sunday, just in light of that not being posted until this past weekend, and us not quite getting through that in the class on Wednesday. Also note that I posted a couple more supplements on Blackboard in the supplemental materials folder. A couple on 3.3, just a couple of notes on computing percentiles and so on. And also the document I mentioned last time on why do we divide by n-1 for the sample variance. Okay, so that's the plan for today. A funny little picture for today. I saw this on XKCD Comics Facebook page. They posted it, and I just thought it was funny because it uses probably a semi-log scale. I don't know if the tasty scale is on a log scale or a linear scale, but we can see that on the bottom here, when we're talking about sphere diameter going from grapes to melons to the moon to the earth, when we have that many orders of magnitude, we're often going to work on a log scale. And kind of as an aside, just something like a little bit related to this, if we think back to say the geometric mean, if we were to say, consider roughly speaking, say the scales of the universe, something like from the Planck length or the Planck length, in the ballpark of like 10 to the minus 34 meters. I think that's about what it is. Or the observable universe, 10 to the plus 25-ish meters, something like that. If I just average these in the sense of an arithmetic mean, it's basically 10 to the 25, right? Because 10 to the minus 34 is pretty much 0. So if I just take half of 10 to the 25th, that's basically 10 to the 25th, right? 0.5 times 10 to the 25 is basically 10 to the 25th. If I want to get a sense of what's in the middle of these two extremes, something like a geometric mean might be a better average. This would be square root of 10 to the minus 34 times 10 to the 25, or this is 10 to the power minus 34 plus 25 over 2. We see that the geometric mean, in a sense, averages the exponents. So this is something I don't think I mentioned this in the supplement. I might have, but this gives us, well, what's that, like 10 to the minus 9 halves, 10 to the minus 4 or 10 to the minus 5, somewhere in that ballpark. Kind of interestingly, the kind of right in the middle of our extremes of the universe is something that's about the diameter of a human cell. So I think that's kind of interesting that like something like the fundamental basis of life is kind of like right in the middle of the Planck length at the extremely small scale end of things, where things that are smaller than that in some manner of speaking can't exist. And on the largest scale, the size of the observable universe, kind of right in the middle, in the sense of the middle orders of magnitude, is kind of the scale of life. Maybe that's a little bit of an observer bias, What's the formula for geometric mean? Right here. For two data points, it's the square root of the product of the two data points. But I don't know. Yeah, I thought that's kind of interesting. There might be a little bit of observer bias. Maybe, if our cells were 10 to the fifth meters wide, maybe we would have observed things further than we've observed them in the universe by now or something. I don't know. Or maybe if we were, 5 orders of magnitude smaller than we were, maybe we would have a different point of view on quantum mechanics, or who knows. But so maybe we're starting from the middle and working out, and that's why we see that, or maybe it's something more fundamental. We'll leave that to the philosophers to discuss, but I think it's just kind of an interesting little tidbit. Okay, and then the quote of the day today. We have talked about some finance stuff, and sometimes the quote of the day doesn't necessarily tie into one of my courses, but I use the same quote for all 3 courses every 2 days. So this one kind of ties a little more closely into something we're covering in another course, but I think it does tie into things that we've talked about in this course before, particularly with financial stuff. That if you think it seems a little silly sometimes that we can get people to do lots of things and put in a lot of effort and give up a lot of their time and energy for what amounts to little slips of paper that we hand them, dollar bills or $100 bills or something, or these days even what amounts to a different arrangement of electrons in some device somewhere. When you log into your bank account and you see that these electrons seem to be arranged in a way that represents $100 more than what they represented yesterday. It seems maybe a little silly. And particularly, we like to look at, some of the folks from thousands of years ago and say, oh, look what they used for money. Wasn't that silly? What we use for money is kind of silly too. But what's the purpose of that money? What fundamentally is that fiat currency? And I think a good point of view is that it's evidence of past productive utility that one has provided to the market that entitles one to future productive utility from the market. This kind of goes in line with that exchange value for value idea that I had mentioned in a previous quote. I think a lot of times we focus on the second half. We say, what's the purpose of money? To get me stuff. But if we think more fundamentally, and I think this is an important idea across mathematics and philosophy in general, is, if I have an idea, can I really dig into that and drive into that and try to bring it down to something more fundamental, more foundational? So I think we typically start by thinking, what's the purpose of money? To get me stuff, but really the purpose of money is to represent utility that I've provided to the market previously, and that's what entitles me to that future value, that utility from the market. So why does somebody do something for this $100 bill? Well, they don't really care about the $100 bill. But that $100 bill is evidence that they've provided that utility to me or to somebody else in the market, and that entitles them to ask that of the market in the future. And my mother-in-law, Cindy, my wife's mom, she had a saying that Jen has remembered all these years, that money is a negotiable representation of your father's time. So again, that idea that, if you go into the store and you say, oh, I want this thing that costs an amount of money, that amount of money is directly tied to productive utility. I think it's a really important idea in economics and in a lot of debates and things in society these days. I think we tend to lose track of that, what that money fundamentally represents. And our government likes to print more money, and then you can think through the implications of that. What does it mean when there are just more dollars available in the market than there were, say, a year ago or something like that, when they're maybe in a time period where they're doing quantitative easing? So lots to unpack there, but I think it's relevant to a lot of our discussions today in society. Okay, so let's continue on with 3.2. Let me just copy these down here because Got that picture in the way. So finishing up 3-2. So the empirical normal rule. So what's the idea of the empirical normal rule? The idea is that at this point, we know how to compute the mean and the standard deviation. I'll write them as mu and sigma, but if this was a sample, we'd be using X bar and S. So we could think of it in either context. I know how to compute the mean and the standard deviation, a measure of center and a measure of variation, or where the typical data point lies, or where the middle of the data is, and how spread out the data is. Can I make a statement about my data points as a whole, about my data set as a whole? Can I say, based on the mean and standard deviation, if I know that, maybe I can say where I think most of my data are going to be located? That's what the empirical normal rule tries to get at. It has an important assumption, an important caveat. If the data set is roughly bell-shaped, in other words, if a histogram of my data set looks more in line with this kind of picture where I have a peak, I'm symmetric about that peak, and I tail off to both sides. If that's roughly true, then I can say the following. Then approximately 68% of the data points will have a value within one standard deviation. That's a goofy looking sigma, within one standard deviation of the mean. Approximately 95% of the data points will have a value within 2 standard deviations of the mean. And approximately 99.7% of the data points will have a value within 3 standard deviations of the mean. So that's the empirical normal rule. If we think about what this means, if we drew a number line here, and we consider, let's say this is the mean, and let's say this distance is 1 standard deviation, then this point on the line would be mu plus 1 sigma. If I went 1 standard deviation further, this point on the line would be mu plus 2 sigma, and 1 further, mu plus 3 sigma. And the same on the other side, mu minus sigma, mu minus 2 sigma, and mu minus 3 sigma. So now I can imagine creating a chart, something like a frequency distribution, where I can think of having different bins. In this sense, it's going to be a little bit more like a cumulative frequency distribution than just a standard frequency distribution. But one bin could be mu minus sigma to mu plus sigma. In other words, this interval on the real line. And I could ask myself, I look at my data set, what's the percentage of the data points, or what's the relative frequency of the data where the value is between mu minus sigma, mu plus sigma. Or what's the percentage of the data points, or the number of the data points that satisfy the criterion over the total n of the data set. What's the criterion that the value is within one standard deviation of the mean? And that should be about 68%, or about 2/3 of my data should be within one standard deviation of the mean. Within two standard deviations should be about 95%, or about 19/20ths of my data. 19 out of 20 data points should be within two standard deviations of the mean. And within three standard deviations of the mean, 99.7%, or about 299 out of 300. Or I could think about this in kind of the opposite way. So about one data point out of three should be outside of mu minus sigma to mu plus sigma, or should be more than one standard deviation away from the mean. So about a third of my data points should be more than one standard deviation away from the mean. About 1 out of 20 data points should be outside of the interval mu minus 2 sigma to mu plus 2 sigma. Or about one data point out of 20 should be more than two standard deviations from the mean. And about one data point out of 300 or so should be more than three standard deviations from the mean. And just a little bit of nomenclature here, a little bit of vocabulary. When a data point is, say, more than one standard deviation from the mean, we call this a one sigma event. That data point being more than one sigma, one standard deviation from the mean. A data point being more than two standard deviations from the mean, we call it a 2 sigma event. And being more than three standard deviations from the mean, we call that a 3 sigma event. So if our data set is bell-shaped, we would expect to see 1 sigma events fairly regularly. If I had a data set of size 10 or 20, I'd expect a handful of 1 sigma events, where the data value is more than one standard deviation away from the mean. If I had a data set of size, 20, 30, something like that, I might expect to see 1, maybe 2 sigma events. And if I had a data set on the order of like 10, 20, 30, I wouldn't really expect to see any 3 sigma events. I wouldn't really expect to see a 3 sigma event until I was getting data sets in the size of hundreds. So this is another way to think about this. So that's the empirical normal rule. This ties really closely into the normal distribution, which we'll cover quite a bit in chapter 6. But for now, this is just kind of our rough take on this. We'll make a lot of this more precise in chapter 6, but at this point, well, what does it mean for something to be roughly bell-shaped? Well, that's going to be a qualitative decision. That's going to be a subjective decision, right? Why is this like approximately 68%? What's the exact number? Well, we'll be able to answer that a little more precisely in chapter 6. But we can see that kind of the majority of our data under a bell-shaped distribution, majority of our data is within 1 standard deviation of the mean, the vast majority within 2 standard deviations, and almost all of it within 3 standard deviations. So that's kind of how we can think about a standard deviation. 1 standard deviation, and most of our data is within 1 standard deviation. 2 standard deviations, almost all of it, and 3 standard deviations, basically everything. It would be quite strange to have more than a couple 3 standard deviation events, unless I got a data set up in the size of thousands or something like that. Okay, so a somewhat related theorem is Chebyshev's theorem. Chebyshev, number one, he probably wins the award for the coolest first name of any mathematician, Pafnuty Chebyshev. Obviously a Russian name from something like 100 years ago or something. So his name is, unfortunately, when you transliterate Russian into English, there's like 1,000 different ways to do it. So sometimes you'll see like a V at the end, but Russian devoices final consonants. So sometimes you'll see an FF at the end, or right. Sometimes you'll see the SH as a CH instead. So there's like 1,000 different ways people spell his name. I think some people put a T at the beginning, like TCH. I'm going to go with this transliteration. I think this is a pretty reasonable one. Other people might disagree. But Chebyshev's theorem says the following. It says for any data set, and I'm underlining any here because remember, for the empirical normal rule, we had the criterion for roughly bell-shaped data sets. That's when we can apply the empirical normal rule. If I have a bimodal distribution or a skewed distribution or something, well, then the empirical normal rule doesn't really apply. But Chebyshev's theorem applies for any data set. It applies much more broadly, but what it says is much broader in a sense as well. It says something that's less specific than the empirical normal rule says. So the empirical normal rule is narrower in scope, but more specific in what it says. Chebyshev's theorem says the following. For any data set, the proportion or the relative frequency of data points within k standard deviations of the mean, in other words, in the interval, or data points with value in the interval mu minus k sigma to mu plus k sigma. So k could be 1 or 2 or 3. So being within 1 standard deviation of the mean, 2 standard deviation of the mean, 3 standard deviation of the mean, kind of like we saw up here. But k could be something else. It could be 1.5 or 2.7 or whatever you want to put in there, more or less. Okay, for any data set, the proportion of data points within k standard deviations of the mean, in other words, what I wrote there, is at least one minus 1 over k squared, where k is bigger than 1. I suppose there's not really anything wrong with plugging in k equals 1, but that just says that the proportion is at least 0, which of course is true. So for Chebyshev, let's look at a couple of different k's. Let's look at, say, 2, 3, and 4. What would be our bin, so to speak, if we were making a similar chart to what we made for the empirical normal rule? What's the interval in which I'm looking for a data value? Well, that's, for this one, mu minus 2 sigma to mu plus 2 sigma, mu minus 3 sigma to mu plus 3 sigma, mu minus 4 sigma to mu plus 4 sigma. These are the bins that we'll use here. When k equals 2, and 1 minus 1 over 2 squared, 1 minus 1/4, that is 75%. That's 3/4. So this is the relative frequency, and this is really the minimum relative frequency. At least, we're going to have at least 75% of our data points that have value within 2 standard deviations of the mean. For 3, we have 1 minus 1 over 3 squared, 1 minus 1/9. That's 8/9, or about 89%. And for 4, 1 minus 1 over 4 squared, 1 minus 1/16 is 15/16. Or that's in the ballpark of 94% or so. So we can see that Chebyshev's theorem applies to any data set, but it sacrifices precision. Number one, we're saying that these relative frequencies I'm presenting are the minimum, but in practice, they're typically going to be much higher than that, where the empirical normal rule gives me an approximation. It says, I think it's going to be around this. So in practice, it should be close to 68, 95, 99.7, where Chebyshev just gives a lower bound, should be at least 75, 89, 94. And then the empirical normal rule, we can see that we're saying within 2 standard deviations, we should have 95% of our data. Down here, within 2 standard deviations, we're only guaranteed to have 75% of our data. So this is a much broader range, right? 75 to 100 is quite a broad range of possible relative frequencies, but saying about 95%, that's much narrower in what it says, and also that's also a much higher number, right? And I think we discussed before in chapter 2 that these bell-shaped distributions come up a lot in practice. So if we're tending to run into bell-shaped distributions, we could use Chebyshev as an absolute guarantee with the lower bound of 75%, but it's probably better to use an approximation of 95% from the empirical normal rule. Why is Chebyshev important? Well, Chebyshev is important because it's going to provide the basis, the foundation for some important theorems later on. And when we want to make a statement about it, when we want to make a theorem, we're making a statement that we want to hold true in all circumstances. We don't want to say something's a theorem and say, well, but it's only really true like most of the time. So Chebyshev gives us this lower bound that is always true. This is true because it's a product of the mathematics. It's the way that the variance is calculated, the way the formula works, the way the formula for the mean works. That's why Chebyshev's theorem is true. So this will always be true, and then this can provide the foundation for important theorems later on that will actually be a lot more useful. And then lastly, the range rule of thumb. A rule of thumb or a heuristic is something that's kind of quick and dirty, easy to do, but maybe not so accurate. The range rule of thumb is that a standard deviation is about a quarter of the range. Or in other words, the range is about 4 standard deviations. And again, if we think back to our empirical normal rule, if we had a data set that was roughly bell-shaped, it's quite unlikely to get a 3 sigma event, right? Most of our data are going to be within 2 standard deviations of the mean, going from mu minus 2 sigma to mu plus 2 sigma. that's a span of 4 standard deviations. So this kind of rough idea that my data set should span 4 standard deviations is going to be an important idea when we come to the end of section 3.3, and talk about outliers and how to find outliers. This idea of saying kind of typical data in some loose sense is going to be within a 4 standard deviation span on the real line. That's going to be an idea that we're going to use to help us find outliers. In practice, I don't think this is a very good rule of thumb to use. If you need to know the standard deviation, either give up and say, okay, I'm not going to know the standard deviation, I'm just going to report the range and be done with it. Or if you need to know the standard deviation and you don't want to give up, then just compute the standard deviation, bite the bullet and do it. But where this kind of rule of thumb comes into play again is really at the end of 3.3. So a couple of these little things, the empirical normal rule is actually pretty important. The other two are really, we're introducing them to really provide a basis for some future work. Any questions on 3.2 before we move on to 3.3? Okay, so moving on to 3.3 then. Measures of position, or sometimes called measures of relative standing. So if we think about 3.1 and 3.2, we were saying, I want to take the whole data set. This might be 10 numbers, 100 numbers, 1,000 numbers. I want to crunch it down to one number, and I want that one number to describe some aspect of the data set as a whole, maybe where it's kind of generally located for something like a measure of center, or how spread out it is for something like a measure of variation. I want to report to you one number that describes some characteristic of the data set as a whole. 3.3 is a little different. We're shifting gears a little bit. We want to describe the position, or the relative position, of one data point, basically relative to its peers. Relative to the rest of the data set. So if I'm going to zoom in on one data point, I'm going to pluck out one data point, and I want to say, where does this stand relative to the other data in the data set? So 2 things about this. One is that this is a different scope, right? We're not looking at the whole data set and trying to crunch it down to one number. We're looking at one data point and trying to describe something about that data point, not the whole data set. So we have to pick out a data point. We would have a different descriptive number, presumably for each data point. Different data points in the same data set are going to have different results. The other thing that might seem a little maybe silly or something here is, well, if I'm only looking at one data point, well, it's only one number. Why am I just going to replace that number with another number? Well, the reason for that is that the number that the data point is associated with is its value, and that's certainly an important number. But maybe we want to say something about that number. Maybe that number alone doesn't give us a good intuitive understanding of what we're trying to understand. And by, say, maybe reporting something like a percentile, maybe that does give us a more intuitive understanding of what that data value represents. So even though we're exchanging kind of one number for one number in this case, before it was very clear when we were exchanging one number for 1,000 numbers, the one number was easier to understand. Here we're exchanging one to one. It might not be so clear right off the bat why that makes it easier to understand. But I think after going through a couple of these measures, maybe we will see the value of this. So we're looking at an individual data point and we're exchanging basically one number for one number, not a whole bunch of numbers crunching down to one number. So I have a couple measures of position. The first is the z-score. The z-score is something we're going to introduce now. It seems like, we'll introduce it and you'll say, okay, I can see that maybe is kind of a nice measure. But it doesn't seem to blow you out of the water. It's not, it's not this great thing. We won't talk about it at all for a few chapters, but then it's going to come back really strongly at the end of chapter 6, or really the middle of chapter 6. So after basically, after the beginning of chapter 6, we're going to use the z-score in pretty much every problem for most of the rest of the course. So the z-score, introducing it now, it'll seem like, okay, that's a cool idea. It's really going to come back with a vengeance in a couple of chapters. So write this down, star it or something. Don't forget about it. A couple of chapters down the road, it's going to come back. And let's consider the z-score for data value x. So this could be a value that is associated with a certain data point, or it could just be a hypothetical data value. We compute the z-score by first subtracting the mean and then dividing by the standard deviation. Oh. And whether we're in a population or a sample, that looks like x bar minus mu over sigma, or x minus mu over sigma, or x minus x bar over s. So just using the different notations for population versus sample, but the idea is the same. We subtract the mean, then divide by the standard deviation. So what subtracting the mean does is it kind of takes the center of the data set and like pulls it back to be centered at 0. And then what dividing by the standard deviation does is it kind of rescales the data set to have kind of a consistent scaling, a consistent variability. So we subtract the mean, we divide by the standard deviation. If we rearrange this, so I have z and x are related to one another. And remember, mu and sigma are characteristics of the distribution as a whole. So, or the data set as a whole. So if I have my data set, I compute mu and sigma, and those are those numbers. That's what they are. If I pick the data value associated with x3, the third data point, I'll get a certain z-score associated with that data value. If I pick a different data value, I'd get a different z-score. I can solve this for x. And see that x is mu plus z sigma. In other words, what z represents, it's the number of standard deviations above the mean for x. Or in other words, I would say x is z standard deviations above the mean. That's what z means. And here I interpret if z is negative, If I'm like -2 standard deviations above the mean, that's just 2 standard deviations below the mean. So that's what the z-score is. On one hand, it's the answer to, for this data value, how many standard deviations above the mean is it? It's z standard deviations above the mean. Another nice thing about the z-score is that it's unitless. The data value x has units of original data, obviously. The mean has units of original data, so their difference has units of the original data, as does the standard deviation. The units all divide out. So kind of like the coefficient of variation, how we were that enabled us to compare across data sets a little more easily by scaling out kind of the size of the data and the units and dividing out the units. Z-score does something kind of similar. Okay, so let's move into percentiles then. What's the idea of a percentile? If you've taken a standardized test of any type, you might have seen that you take, say, the SAT, let's say, and you score a combined score of 1,050. You're like, okay, I mean, I got a 1,050, right? That's my data value. But I don't really care about that score, that 1,050, right? That doesn't tell me a whole lot. What I really care about is, how does that score compare to the other people who took the test around the same time as me? If I score 1,050 on a scale of, I think it's like 200 to 1,600, something like that, and if that's better than most other people, I'd be quite happy with that score. If it's worse than most other people, I might not be so happy. If it's in the middle, I might be moderately happy with that score. So sometimes the actual data value doesn't really tell us what we really want to know. Sometimes that, SAT score or that raw score on a test doesn't tell me, it's not super informative. But what I really care about is where that stands relative to, in this case, the other folks who took the exam. So what's the idea of a percentile? I want to say, or I want to determine, what percent of the data set is below or has value less than X. And here again, just like up above for the z-score, we'll compute a z-score for a data value X. For percentiles, we'll do the same. We'll compute a percentile for a data value X. And for our discussion, we'll think of X as being a value that's associated with a specific data point in the data set. You can relax that assumption, but you have to build in a little bit more math to do that. So for our purposes, we're just going to assume that the data value that we're interested in is a value that's associated with one of the data points. So let's take, for example, scroll all the way back up here to my data sets. Why am I having so much trouble selecting these? There we go. Apparently it is not a good copying day today for OneNote. Okay, there we go. So let's take a look at the Ashley data. And let's say that I would like to know the percentile associated with the data value 7. Or in other words, 7 is at what percentile of this data set? So I'm going to find, is what that says. Find the percentile associated with the data value 7. Well, the first thing that I probably want to do is, again, sort my data set. So I have 5, 7, 8, 9, and 11. So I see that the data point with value 7 has a higher value than one data point and a lower value than 3 data points. How do I assign a percentile to this? How do I assign a number between 0 and 1 or 0 and 100%? Right? A percentile is a number between 0% and 100%, again, representing what percent of the data is below X. I'm going to put below kind of in quotes here. Should this be a strict inequality, a non-strict inequality? We're going to discuss that in a minute here. So the first thing that I would like to do is take the data set as a whole and try to assign to each data value some swath of the real line between 0 and 1 or 0 and 100%. I would like to allocate this real line equally to each of my data points. I have 5 data points, so I'm going to create 5 equal intervals of this chunk of the real line between 0 and 1. So my tick marks or my dividing lines are going to be at 0/5, 1/5, 2/5, 3/5, 4/5, and 5/5. 0/5 being 0 and 5/5 being 1 or 100%. 1/5 is 20%, 2/5, 40%, 60, and 80%. Then I'll take each of my data points, starting with the ones with the lowest value, and I'll assign each one to one of these bins, so to speak. So the first data point, x1, with value 5, it kind of, owns the property from 0 to 20%. 7 kind of owns the property from 20 to 40. 8, 9, and 11. So I can draw out this chart. And now I have a visual representation that can really help me answer questions. So I could ask a question like, we're going to come back to this one in a second here. I could ask what data value is at the 37th percentile. How do I answer that? Well, I go to 37% on my index from 0 to 1. And I see that's associated with the data value 7, or 7 returns per day. So I can look up really quickly what data value is associated with the 65th percentile. Well, that's going to be 9. Or the 92nd percentile, that's going to be 11. I do have this annoying detail, though, with percentiles. What data value is at the 28th percentile? Well, that's also 7, or the 21st, or the 39th. There are a lot of these kind of forward questions in a sense. What data value is at blank percentile? There are a lot of different questions like that that yield the same answer of 7. This is not a one-to-one function. In other words, if I was to look at percentile going across the x-axis here and data value on the y-axis from 0 to 20, I have data value 5. And then from 20 to 40, 7, 40 to 60, 8, 60 to 80, 9, and then the 80th to 100th percentile, 11. So I have a step function like this. If I'm going this direction, if I give you a percentile, pretty much you can tell me what data value is associated with it without too much trouble. But there's a couple of nuances that we might want to deal with here. If I give you a data value, if I look at the inverse problem, where I give you a data value, that's a little bit high. So I give you a data value of 7, and I ask you what percentile would generate, in a sense, that data value, that output of 7. So I'm looking to invert this process, but I don't have a one-to-one function. This is not a well-defined question, right? I could give an answer to the left side over here, or to the right side, or somewhere in the middle. Those would all be inputs that generate an output of 7. So when I ask a question like find the percentile associated with the data value of 7, it's kind of unclear what we mean. So one thing I could do is I could report kind of this leftmost endpoint. Coming back to our initial question about what is a percentile, it's the percent of the data set below, in a sense, X. If I reported the left endpoint 20%, or the left extreme of kind of 7's property, so to speak, I have one data point that has value strictly below 7, data point with value 5. Out of 5, 1/5 is 20%. So if I report the left extreme of 7's property, so to speak, then I'm interpreting this below here as a strict inequality. That's how our book does it. But about half of the intro books seem to interpret it differently. I could instead choose to report the right extreme. I could choose to go to the right extreme of 7's property and report 40%. So I would include all of the property, so to speak, for the data values less than 7, but also all the property for 7. That would interpret below as meaning less than or equal to a non-strict inequality. And again, from what I've seen, maybe roughly half of the intro textbooks choose the left endpoint and half of them choose the right endpoint. Maybe roughly half of them choose strictly less than and half of them choose less than or equal to. But choosing either of these extremes maybe doesn't seem really so sensible for a couple reasons. One, we're going to see in a little bit here that we want to define the median, which we already know how to compute from section 3.1, we want to define that as the 50th percentile, the middle of the data point in that sense, in the percentile sense. But if we're defining the median as the 50th percentile, when there's kind of a tie, loosely speaking, we average things together, we take the middle. Why don't we do that same thing here? Why are we taking the left or the right extreme? We also probably don't want to introduce bias. We don't want to introduce some kind of estimator bias where when we have a sample that's a small sample, and then we choose, am I going to choose the left extreme, the right extreme, somewhere in the middle? If I always choose the left extreme, and I say that 7 is at the 20th percentile, that's my sample estimate. When I move up to a population, is that likely to hold true, or is that likely to be a biased result? Well, I think if we're always choosing the left endpoint, we're going to see 0, 20, 40, 60, and 80. We're never going to see any results from 81 to 100 in this type of a setup with a sample of size 5, but we will see a result down here at 0 every once in a while. I think it's pretty clear that that's going to introduce some negative bias. Well, reversed one too far. Same thing if we chose always the right endpoint. Now, for scenarios like the SAT, they don't care so much about this because the number of data points they have is way larger than 100. So basically, they can just allocate, like, if you had 100 data points and 100 percentiles to cover, well, you could just allocate 1 percentile to each data point, and then you have a much more well-defined process, right? You have a function down here that's much closer to being 1-to-1. So we have to make some concessions. And again, some books interpret below as strict less than, some interpret it as less than or equal to. I think the best way to go about this to maintain consistency with things like the median, with things like unbiasedness, which we've already harped on quite a bit and we'll come back in chapter 7. I think what we should do is we should pick the midpoint of 7's territory. This is going to give us an unbiased estimate. This is going to give us something that feels more consistent with things like how we define the median and so on. So if I have to choose a percentile to associate with the data value 7, I'll go for the middle of 7's territory. I'll go for the 30th percentile. If I do this on the chart, it's pretty easy to find. If I wanted a formula for this inverse problem, the percentile would be the number of data points with data value below X. And by here when I say below, I mean, just to be completely clear, strictly less than X. If we just took this and divided by n, the total number of data points, we would get the left bound answer, the left biased answer. If we made this a less than or equal to, we would get the right biased answer. And to split the difference, we just add 1/2 of the number of data values that are equal to X. I don't want just the strict inequality, kind of taking into account none of the data values that are equal to X. I don't want the non-strict inequality taking fully into account all the data values equal to X. I want to split the difference with the 1/2. Or in this application, I have one data value less than 7 I have one data value equal to 7. 1 plus 1/2 is 1.5 over n equals 5. 1.5 out of 5. Well, that's 3 out of 10. That is 30%. All right, let's go through a second example. We'll use the Brandon data here. Again, data set of size 5. So this is going to feel pretty similar to the actual data. I want to put one fewer tick mark than I have data points, roughly equally spaced. So 4 tick marks in between 0 and 100% divides my interval into 5 subintervals. 0% is 0/5, and then I have 1/5, 2/5, 3/5, 4/5, and then 5/5 here at the end is 1 or 100%. 1/5 is 20%, 40, 60, and 80. And then I'll look at the Brandon data, and I'll start with the data point with the smallest data value. That will go in the leftmost bin, and I'll work my way to the right with increasing data values. So if I have a data set, say of size 10 or below, taking this graphical approach, I think, is definitely the best way to go. Using all these formulas that the book gives, using, say, this formula, or the formula for the other direction, the data value that's at a certain percentile is even more complicated. You have to do, this thing or that thing, whether or not some quotient turns out to be a whole number or have a decimal. Right? It's this process is even messier than just applying this formula, but I think either formula is more difficult than just drawing out the picture. And this is one of the things that I discussed in the supplement on Blackboard. So here, if I wanted to say what data value is at the '67th percentile, again, I would come up here, look for where is 67%. That falls in 11's territory. So the answer is 11. So my data value associated with the 67th percentile is 11. Or if I wanted to ask what percentile is associated with the data value of 14, note that we usually don't like to say that something is like 0% or 100%. That's a bit extreme. And if we were always taking the left endpoint, one of our data values would have a percentile of 0%, the 0th percentile. If we were taking the right extreme, then our answer here would be the 100th percentile. And neither one of those really feels right. I don't want to say that something's at the extreme, especially if I have a sample. That really doesn't seem like something that I ought to do. But I look at 14 here. The value of 14 covers 1 bin's worth of territory, 80 to 100. The midpoint of that is 90, the 90th percentile. So I would say that the data value 14 is at the 90th percentile in this data set. And likewise, the data value 3, for instance, would be at the 10th percentile. Okay, what if I ask the question, what data value is at the 60th percentile? What if I'm right smack on the boundary between the territory between two different data values? Or in other words, how do I handle these jumps here? Up here when the percentile is 20, which data value do I choose to output? And here again, it might seem reasonable to just like always pick the left one or something, or always pick the right one, or flip a coin or whatever. But we're going to do, particularly to stay consistent with the median, which we want to define as the 50th percentile, we're going to average those two neighbors. We're going to average 7 and 11. 7 plus 11 over 2, 18 over 2 is 9. In effect, what we're doing is we're saying these are both open, and we're going to put a point right in the middle. It's a little hard to see that point, but this might seem like kind of a silly thing to do, just dotting in all of these points. But again, this is to maintain consistency for the definition, particularly for the median. So if we're right at a boundary that's shared between two different data values, we average them. Now, we could have had a fraction here, like whatever, 3/7 or something. I think that's about 40-ish% if I had rounded to the nearest 10% or something. I might have rounded these numbers in a different scenario, and then if I was asking a question about one that's close to the boundary, I'd go a little bit deeper. I would just investigate, okay, is that a little bit to the left or a little bit to the right of the number that I wrote there? But here, 3/5 is exactly 60%. We're asking for exactly the 60th percentile, and we average the two neighbors to get that. Again, I think all of this is so much clearer when you just draw out the picture. It becomes basically just the table lookup instead of applying all of these formulas that the book gives. Are there any questions so far in percentiles? Okay, let's look at the salary data then. The salary data has a different size, so the tick marks are going to be at different locations. So the salary data has size 7. I want to take the interval from 0% to 100% and divide it into 7 equal subintervals. I need 6 tick marks to do that. Zero percent is 0/7. And I'll work my way all the way up to 7/7. The fractions with 7 in the denominator have this interesting characteristic. One seventh is 0.142857 repeating. 2/7 is 0.285714 repeating. So as we go through the sevens, we get the same thing repeating. Note that like the 2857 just kind of moved to the front. and the 1,4 to the end. So we just kind of like permute in a sense, but it's a little more strict than just a random permutation. But we just kind of permute this, these 6 numbers repeating here. They're always in the same order. We just change which one we start with. So this is about the 14th percentile, the 28.5, or we'll call that the 29th percentile. 3/7 would be, well, 3 times 14 is about 42, so it's 428,571, or that's about the 43rd percentile. And then what I typically do, just to keep things symmetric so that I'm rounding things the same way and all that, I see that 1 up from 0 is 14. 1 down from 100 should be 100 minus 14, or 86%. 100 minus 29% is 71%. And 100% minus 43% is 57%. Okay, so that gives me my indices. Now I'm going to come through, start with the smallest data value. And I have 3 lots of 28. Each of them gets their own territory. I don't like write 28 and then move to 30 for the next one, right? I get this 28, this 28, and this 28. Then 30, 55, and 100. So I could ask a question. What data value is associated with the, let's say, 78th percentile? And see that 78% falls right in 55's territory. So 55 is at the 78th percentile. I could ask what data value is associated with, let's say, the 40th percentile. I see that corresponds to this 28. Let me undo that circle, clean it up a little bit. Now, something interesting that happens here is I could ask a question like, what percentile is associated with the data value 28? Here I see 3 28s. But remember, I'm always writing these down in increasing order, so the 3 28s are always together. They're always contiguous territories. If I have the same data value written multiple times, the territories are all right next to one another. Well, 28, that value covers the territory all the way from 14 to 57%. I want to pick the middle of that, the same way that I would do if I asked what percentile is associated with 100. I would pick the middle of 100's territory. 28's territory just happens to span 3 bins. So what's the middle? 14 plus 57 over 2. So what's that? 67, so 71 over 2. Or that's 35.5. We'll call it the 36th percentile. So again, I think if you can draw out the chart, the picture, it just makes it so much easier to answer all these questions. When there's some ambiguity, just kind of take the middle or take the average of the extremes. And that's how we resolve the ambiguity here. The philosophy is much more consistent than using, the left hand all the time or the right side all the time. We maintain consistency with bias and things like that, with being unbiased and things like that, and also with the calculation for the median. Okay, so let's look at one last example. So let's say that we have a list of survey results, a list of 6 results. These were, how well did we do? 1, 2, or 3. 1 poorly, 2 okay, 3 great. So let's draw out the picture again. I'll go a little quicker this time. I know 3/6 is exactly 1/2 or 50%. 2/6 is 1/3 or about 33%. 1/6 is about 17%. And then I can come down from 100. 100 minus 33 is 67. 100 minus 17 is 83. My survey results are already sorted, so I can just start assigning them to the different bins. And I see I have an important detail here that because I have an even number of data points, well, my 50th percentile is exactly between 2 data points. So what data value is associated with the 50th percentile? This 50% is exactly on the boundary between these 2 neighboring data points. So again, I average them. 2 plus 3 over 2, 2.5. That's my 50th percentile. When I have an even number of data points, my 50th percentile, which again, we're going to associate with the median in a minute here, my 50th percentile always is right smack between 2 neighbors, and I have to average those neighboring values. When I have an odd number of data points, the 50th percentile always falls strictly within the territory of one of the data values. So then there's really no ambiguity, right? So we're often interested in finding the 50th percentile, sometimes also the 25th and 75th or 10th and 90th percentiles. But particularly the 50th percentile, when we have an even number of data points, we always have to average those neighbors. So a little bit of nomenclature, and that is quartiles. So we have percentiles, kind of per cent, per 100, right? So percentiles kind of go in increments of 1/100. So we have a first percentile, a second, a third, a fifth, a 10th percentile. You don't usually see something written as like, 17.35 percentile or something. Occasionally you might see like, oh, this was at the 99.9th percentile, just to indicate that it's like really high up there. But usually percentiles are reported as whole numbers. Quartiles, so quarter, a quarter is 25%. Q1 is the 25th percentile, and we call this the first quartile. So when I write Q1, Q1 is the data value associated with the 25th percentile. What's Q1 for my survey results here? 25% is between 17 and 33. Q1 equals 1. The first quartile for my survey results is 1. Q3, let's do Q3 next. It's the 75th percentile, or it's the third quartile. 3/4 is 75%. I see 75% is in this bin. Note that the quartiles, there's a nice symmetry here. My first quartile is the second bin up from the bottom. My third quartile is the second bin down from the top. So if I have a bigger data set and I go through the trouble to figure out where is Q1, I can count up from the bottom and say, okay, Q1 in this case is the second smallest data value. Q3 is going to then be the second largest data value. We have a nice symmetry property here, and we can leverage that. There's a saying, I forget who said it, but a kind of a famous saying in math that when a symmetry exists, often the mathematics rewards you for recognizing that symmetry. So in other words, instead of having to go back to basics and compute Q3 from first principles, I can just count from the top down instead of from the bottom up if I recognize that symmetry. Q2 is the 50th percentile. But I noticed the 50th percentile is either, when I have an odd number of data points, it's the middle data point after I've ordered them. Or when I have an even number of data points, it's the average of the two middle data points after I've ordered them. Well, that's just the median. So the median is kind of inherently related to these percentiles and quartiles and things like that. So the median here, the 50th percentile, the average between 2 and 3 is 2.5. So why do we do this silly thing with like averaging the two neighbors? That seems like, it seems a little bit like we were so vague for all of the, 0 to 20 or 20 to 40 or whatever. And now all of a sudden we're so precise about how we want to handle exactly, say, the 20th percentile here. That seems a little silly. But really the reason is consistency with the median, so that we average the neighbors whenever we're computing the median of a data set that has an even number of data points. And when we compute that and we compute the 50th percentile, we get the same answer because we want to define the median as the 50th percentile of the data. A lot of times with skewed data, that can throw off measure of the center, say like the mean or the mid-range, it can pull those towards the direction of the skewedness. We want to use the measure of center, the median, or the second quartile. And then we'll see that, the mean is kind of inherently tied to standard deviation. Sometimes when we have outliers, standard deviation has some problems too, because standard deviation is very closely related to the mean. And we know that those ideas are kind of heavily influenced by outliers. Sometimes to give an idea of the variation, we'll use the quartiles if we think the data is skewed. Or sometimes we'll use the quartiles in conjunction with some other ideas to actually look for outliers, the interquartile, 1.5 interquartile range method. So that's something that we'll see in a little bit here. And then last little detail. And percentiles, deciles, decimal like tenths. So for instance, D1 is the 10th percentile. This is the first decile. Most people would just call it the 10th percentile. D2 would be the 20th percentile, the second decile, down to D9. The 9th decile. Something that you'll often see in economic data, again, that tends to be skewed, tends to be right skewed. You'll often see the median as a measure of center, and then a report of the first and third quartiles, and the 10th and 90th percentiles, or the first and 9th decile. That gives you kind of an idea of the middle of the data, the kind of rough spread of the data, using, say, first to third quartile as something like a standard deviation, something akin to that. And then first and 9th decile is kind of an idea of the extremes, right? It's something along the lines of like a max or a min, but I don't want to report an actual max because of the rate skewedness. So I kind of cut off that top 10%. So kind of the maximum, like kind of standard, kind of normal data point, and then the minimum kind of normal data point cutting off the bottom 10%. So when we have things like skewed data or bunches of outliers, a lot of times you'll see these 5 numbers, Q1, Q3, the median, and the 10th and 90th percentiles, the first and 9th deciles, reported because those are less influenced by outliers or by skewedness. Any questions so far? Okay, so I want to now talk about, to wrap up chapter 3, outliers. We've talked about these a couple of times already. We introduced the idea in chapter 1, and chapter 2, we talked about the idea of skewedness, meaning outliers to one side or the other. Earlier in chapter 3 and 3.1, we had a method of detecting outliers. So our kind of most naive method was look at the data set, and if we see a skewedness, because skewedness is presence of outliers that are primarily on one side of the distribution and not the other, if we see skewedness, there has to be outliers. Okay, well, that's good. But that was just looking at a graph. In chapter 3, or really 3.1, we made that a little more objective. If the mid-range is much bigger than the mean, is much bigger than the median, that's an indication of some right skewedness. And again, if we have right skewedness, we have to have outliers by definition of skewedness. And of course, all of this works with less skewedness as well. I'm just using right as an example. But the chapter 2, like look at the picture and decide if you think it's skewed, is very subjective. 3.1, well, it's objective whether the 3 measures of center line up this way. But if I have a certain mid-range that's bigger than a certain mean, that's bigger than a certain median, are they far enough apart for you to say that they're much bigger than one another, indicating skewedness? Or do you think they're pretty close to one another, even though they happen to line up that way? Maybe that was kind of just by chance. A little more objective in 3.1, but not very objective. We have a completely objective way to evaluate skewedness. And here we'll use the Pearson coefficient of skewedness. Now, something to note is this is completely objective in the sense that if everybody does all of the computations according to the formulas and does them the right way, everybody will come up with the same answer, that the Pearson coefficient indicates right skewedness, or the Pearson coefficient indicates a lack of skewedness, or something like that. That doesn't mean that, if the Pearson coefficient indicates right skewedness, that's the be all and end all, and we determine that the thing is right skewed. So the Pearson coefficient, it's completely objective in the sense that when you compute the Pearson coefficient, you'll get an answer that should be the same as everybody else's answer for what the Pearson coefficient says. But then there's the question of, okay, the Pearson coefficient says this, but that's not the definition of skewedness. So the Pearson coefficient might give evidence in favor of right skewedness. That might be a point in favor of, say, right skewedness. But then if you back up a little bit and you say, do I think the data set is right skewed? You might want to take a more holistic view to answer that question more thoroughly. But the Pearson coefficient, I think, is going to weigh heavily in that argument, or should anyway. The Pearson coefficient is 3 times the mean minus the median over the standard deviation. Here I'll use X bar and S, but of course we could use mu and sigma as well if we wanted to. So I compute this number and I compare it to plus or minus 1. If the Pearson coefficient is bigger than 1, that indicates evidence of right skewedness. What makes a large positive Pearson coefficient? Well, the standard deviation is always positive, essentially, as long as we don't have all of our data values being exactly the same. 3 is, of course, a positive number. So to get a big positive number out of the Pearson coefficient, X bar has to be much bigger than the median, right? If the Pearson coefficient is less than -1, then we have evidence of left skewedness. Again, 3 and S, 3 and the standard deviation are both going to be positive for all intents and purposes, and getting a number that is to the left of -1 means that X bar has to be quite a bit less than the median. And otherwise, in other words, if the Pearson coefficient is in -1 to 1, there's a lack of evidence of skewedness. So this is our decision criterion. And kind of as an aside, the 3 kind of seems strange here. Like, why is there a random 3 tossed in there? If I compare this to 1, in other words, if I compare this to the borderline case for right skewedness, I see that really what I'm saying is that if the mean minus the median, if that's bigger than a third of a standard deviation, if the mean is more than a third of a standard deviation above the median, that's kind of my cutoff for much larger than, in a sense. Much larger than, in the sense of the Pearson coefficient, is a third of a standard deviation. All right, are there any questions on this? So when we come back, we'll compute the Pearson coefficient for a couple of our data sets. We'll see if we think there's evidence of right skewedness or left skewedness or lack of evidence of skewedness. And then we'll note that we want to talk about outliers in general. If there's skewedness, then there are outliers. But we could have outliers that are symmetric, that there's some on the left and some on the right. So a measure for skewedness isn't always going to pick up on outliers. So we want some additional idea or ideas that will help us to determine whether there are outliers kind of outside of the context of skewedness. And as another note, if I do conclude that my data set is right skewed, if I look at a particular data point, I don't know whether that one is an outlier or not unless it's the max. If I have a right skewed data set, the one furthest to the right has to be an outlier by definition. But even the second biggest, I don't really know. So I'd like to develop a measure that also can look at each individual data point and assess it to determine whether it's an outlier or not. So that's going to be the plan for next time. And then we'll move on to chapter 4.